Today's episode is called Buying Quality with Tokens. Reflection and planning are trades, each with a price tag and a documented failure mode. So, let's start from where the last episode actually ended. So, the invoice agent failed the deterministic check, so you run it again, right? You have your second attempt, and what would actually happen is that nothing was learned. You get the same fail. So, and the reason for this is that the loop has no mechanism for learning from the first attempt. So nothing was written down. And here there are two ways to do this. The first one, which is reflection. Second one is planning. So reflection, aka look back, is the idea that you let the agent write down what went wrong and try the whole task again. And look ahead, which is planning, is you make it work out the entire route first, then execute the steps cheaply. And here we need to realize that neither one of them makes the model actually smarter. Both are basically the same move. You are spending more tokens and more work log time in exchange for a better answer. So today we're going to treat them the same way. We're going to explain what they are mechanically, what they cost, and exactly where they break, because both failure modes are documented by the people who invented them. So actually, Reflection has a canonical paper, and the paper is more specific than what we are currently seeing in the market. It says there are 3 distinct models, and people mostly talk about 2 of these, but we will talk about all 3. The first one is the actor. The job here of the actor, and this is quoting the paper actually, is it generates text and action. So it's basically the agent that you already know that is basically attempting the task. Second is the evaluator. So the job of the evaluator is to score the outputs produced by the actor. Note the wording here. It scores. It's not vibing or saying. It's basically, as the name states, it's an evaluator. It gives a grade. And we will come back about this grade later on. Where it comes from, this is something we will talk about later on in the episode, because that's very important. Let's talk about the third part of the model. Here is the self-reflection model. The job here is to generate verbal reinforcement cues. So it reads the failed attempt. Let's say you have a failed attempt and the score, which are these 2 elements. And from there, it will write a sentence about what went wrong. And that's basically what we call an episodic memory buffer. So it's plain text kept outside of the attempt and the grade. And the idea here is that actually with the dashed line is that it re-enters the actor context on the next trial. So, and that loopback is the entire mechanism. The point of this whole thing is that loopback. So, which gives you 2 kinds of memory. And this split is worth holding. So you have the short-term memory, which is the trajectory of the current attempt. So what you're seeing here, and then you have the long-term one. Because this short-term memory actually dies. This part will die between the attempts. Long memory one is stored reflections, and this will be surviving each attempt. And this will be controlled by this self-reflection model. So here, this is what people get wrong about this pattern. It's not a critique inside one answer. The unit as a whole is a trial. So this is a trial in itself. The agent attempts the entire task, start to finish, and then gets a certain grade. Trial 1, and the evaluator says fail, for example, here. So it's either 0 or 1. 0 is supposedly here, will be coded as fail. Now the conversion, and this is something you need to think about, is that you're converting the 0 or 1, this grade that was given by the evaluator, into verbal feedback in the form of a textual summary. Why it was this a failure, giving certain assessment to that failure. And this is added as a context to the next episode, to the next trial. So trial 2 here will not be a rerun. It starts with that lesson that was already learned from the previous trial, and it's already sitting in the prompt, and the control flow is a plain loop while the evaluator has not passed. So let's say we are under the trial cap and we run the actor with memory. After that, what we do is that we are appending a new reflection every time we have a new trial. It's a loop. That's the whole thing I want you to keep in mind. You're looping through every trial. And this is why the paper calls it verbal reinforcement. We reinforce the agent, quote, not by updating weights, but instead through linguistic feedback. Of course, this can only be done with agents that are LLMs, like linguistic agents. So there is no training run, no fine-tuning. This is all engineering of your architecture that you will be using for your agentic systems. So the agent gets measurably better across different attempts because every time you're having different lesson, while the model itself never changes at all. So here, what is in that buffer? So this text here is quite illustrative. So the mechanism, you need to look here. Let's look at this example. So you have invoice number 4117. And here I compared invoice quantity. This is what your evaluator will be saying. I compared invoice quantity to PO quantity and concluded over billing. Okay. I never read the goods receipt. Next time, read goods receipt before concluding. So that's what we are having as lesson from the first trial. So here, the causal reason helps us for the next trial, of course. And on trial 1, the prompt was basically system plus task. On trial 2, the prompt is system plus task plus that sentence that we had here. So the model is not restarting from zero. It's not trying harder, You're giving it more context. And 2 bounds, both from the authors. And for this methodology, first, memory is capped. So they bound memory by a maximum number of stored experiences. This is what we call omega. And they said this between 1 and 3. Usually it's dependent on the context limit. And as you can see here, this is what we call a FIFO queue. First in, first out queue. So when you're bringing a new memory here, the first one, let's say you're bringing mem4. The first one that came in, let's say memory 1, will be dropped. So that basically doesn't accumulate, and you're trying, the idea is that the first lessons will not be as valuable as the later ones. Second bound, and they say this plainly, is the approach relies on the power of the model self-evaluation capabilities or heuristics and has no formal guarantee for success. This is something you need to hold on because there are models that are better at this self-evaluation thing than others. My own experience is that Opus 5, for example, in 2026, today in August 2026, really sucks at this self-evaluation. It talks too much, it adds too much. So here you need, my opinion is not even what the companies are releasing in their benchmarks. You just need to talk to other engineers and try to think which models will give you this exact balance between context and not being too talkative. So and also the pricing comes into that. So it's really engineering work. It's not about science. This is something you learn with experience and talking to other engineers. So with all of this reflection, what are you basically buying? I just need you to remember, like the ballpark, you don't need to remember the exact numbers. So on HumanEval, this is a benchmark, you are having 11% improvement compared to the previous state of art of GPT-4, which is at 80. So this is the methodology that was used by GPT-4. So it's not really a rounding error improvement. It's sizable, On AlphaWorld, another benchmark, decision-making plus 22% absolute. And concretely, 130 of 100 and 134 tasks completed. So on HotpotQA, you're having 20% improvement. I just need you to remember one thing. So if you read the shape of the gain, it's not just the size. These curves run over roughly 10 to 12 trials. So you're having with a spike between the first two. This is something we discussed already about in the previous paper where in the previous episode where we have spoken how when it comes to reflection or LLM as a judge specifically. It's the first two trials that count. After that, you're really having diminishing returns every assessment round. Some people would tell you, hey, there are emerging capabilities that could emerge, or if you put the temperature low or high enough, you might find something interesting. I disagree, frankly, especially in enterprise context. If cost is part of the things that you need to think about, it's only the first one or two rounds that count really, or first two trials that count for your best result. The other ones might bring some marginal returns, but not worth it for your task. Now, this is something you need to put in your head, and this is the reason why many enterprises out there were trying to use agentic AI and were failing. So look at what actually played. So the evaluator in each of these benchmarks. So in code, this one, you had self-generated unit tests. You run them, they pass or they fail. And that's like external feedback to what you're building. In AlphaWorld, the environment owns success signal. In HotpotQA, you have exact match grading between trials. So not one of them is the model asking itself how it did. We are not really doing LLM as a judge here. This is the point that I keep on hammering over and over again in this series. All three are external and verifiable. All these three are outside signals. The reflection is only ever a translation of a real signal into words. So, and here is what happens when you remove that. Let's say here you have refined bench, which is, I believe it was a paper, and you have 1,000 problems. Frontier models here would score modestly to begin with. You have Gemini 2.5, and you have also GPT scoring the following scores. On the other hand, if you let them iterate on their own, unguided, Gemini gains 1.8% across the iterations. DeepSeek 1 goes down by 0.1%. Now that is the cost of a reflection loop with no real grader. You pay for every extra turn, and you get noise, actually. You might actually lose performance. Same paper, flip one variable, hand the model targeted feedback instead of asking it to look again, and refinement reaches near perfect within 5 turns. You're not getting more gain. So the rule is no signal, no gain. A reflection loop with nothing real grade in it is a token build with a story attached. This is the reason why enterprise AI fails, and there are many companies like Uber who are actually just spending money for the sake of it. Now, let's look at the other philosophy, let's say it. You're spending the tokens up front, and here what you're doing is that the framework relies on two things. You have a planner and an executor. So this is your planner, this is your executor. Your planner is a big, expensive model, and it's called once, and it writes a list of steps. It says, okay, you're going to do 1, 2, then 3. This is what usually people do when they are coding, actually. And the executor is a smaller, cheaper model that carries out each of these steps. So it's going tack, tack, tack. And there is a third piece people forget, and which is the replan. Once execution finishes, the planner is called again with a replanning prompt, and it decides whether to finish or write a follow-up plan if the first one did not have the desired effects. Well, this is actually what usually happens in coding, or what we call also vibe coding, actually. Without that step, this pattern cannot recover from anything. So what you're buying here is you have faster execution, cost efficiency. You're swapping here, instead of having to use for the executor big model, you're swapping for like a smaller one, which will be your executor. The issue is that the major downside of this approach is that it takes a lot more calls. Here, from the beginning, we're planning on having more calls than the basics. So the economics are bet here. You avoid a big model call at every single step, but each replan buys you one back. Plan first wins you when reality basically cooperates. What does this mean is that if actually things work out, you might win calls by the end of this. So you're not even really sure about that. We will discuss this later on, of course. So what's the point of this whole thing? Why does planning actually work at all here? So the academic anchor is plan and solve. So you devise a plan that divides the task into smaller subtasks, then carry out the subtasks according to the plan. And that paper exists for a good reason. Its authors sat down and counted why plain step-by-step reasoning fails. So here you have the zero-shot chain of thought measured error types. You have these 3 error types. And of course, planning attacks one of these bars, which is, of course, the missing step errors. Why? Because when you're writing the steps first, the model cannot skip a step that is already written, like the executor here. And this wins you those 12%. The issue is that, so here you're actually buying completeness, not really comprehension. Your planning does not do anything about these 27% or 7%, which is a big issue for us. Because what happens mostly is that the plan is not correctness guarantee. Your result is bounded by the quality of the plan. And the confidently wrong plan gets executed confidently here. At speed, by a model, by cheap model that has no idea what the hell it's doing. The design time version of that failure is its own episode. We will talk about it later on in episode 9. But this is the paper that should be the reference. So keep this in mind. You're always, this is what people usually say, hey, prompt better, because many of the times you're having a semantic misunderstanding, or you actually asked your question in the wrong way to your own model. Now, this is an extreme version, and this is a part where we should talk about. This is the ReWOO, the reasoning without observation architecture. So you have 3 modules named in a paper, and these modules are the planner, the worker, and the solver. The part that is interesting here is that the planner writes when it does not yet know any answers. So basically, in an example, this would look like this. You have an artifact, like data, and the plan would read and have these 3 actions, like read the purchase order, read the goods receipt, and compare the quantities. And what it would do is that it would store E1, E2, E3. It's basically saying, hey, in each of these hashes, it creates a placeholder. It's creating a promise to fill in evidence later. The plan can reference results it does not have yet. And that's what's nice here. So then the worker would goes and populates these placeholders with real evidence, and the solver reads all the plans and all the evidence together to write the final answer. Notice what never happens here is that the planner does not see a single result. It wrote the whole thing blind, especially here, as I told you. It's basically just creating these placeholders. And the whole entire distinction here is that the loop had an observation between actions. So reality entering after every step. ReWOO is gonna be deleting it here. So that's what we lose. That one deletion is basically a pattern. On the other, and what creates it has a bonus, because the whole plan exists up front. Steps here can run with no dependency between them, but that dependency could create some extra results. So it has its positives and it has its negatives. So here hash E1 and hash E2 are parallelizable, not automatically parallel. And this is something that you need to figure out for yourself, is that if the dependency relationship between every one of your actions matters or not. And this is the paper that I'm talking about here, the ReWOO paper from, if I'm not wrong, I forgot which year, but from these writers. So why use ReWOO here instead of React, for example, which is from episode 7 or 6? So this is the headline. You have on the HotpotQA benchmark, you have 5 times more token efficiency and 4% accuracy improvement. Now, also in numbers, here you can see if you're using React loop that we have already discussed in our previous episodes, you're having this amount and this amount of tokens used in the reasoning process for each loop. So the loop resends for React, the loop is resending its whole history every step. So input grows with every lap. And on the other hand, ReWOO makes one planner, so nothing gets rebuilt. And here you have to see that 64% average token reduction across 6 public benchmarks with 4.4% absolute increase in absolute accuracy. So you're not really here sacrificing quality for, at least not, depends on the public benchmark. And in money, as you can see here, for HotpotQA, you're spending a lot less money with ReWOO than compared to the React loop. So here, you need to understand that this is just an example that's basically for certain tasks. As I told you previously, if between every run, every trial, you having the dependency between every trial is very important for your process, then you shouldn't use ReWOO. Then still, the React loop is still the correct one, even if it costs more. But if you think it matters less and maybe it's not as complicated of a process as you want, but still needs recursion or the loop effect, then the ReWOO loop could be better. So it's really a case by case. It's really that dependency between every trial that will make you take the decision if you're gonna go with the ReWOO or with the React loop. So here you need to be careful. There is an obvious criticism of ReWOO and people get it wrong, and actually you should be corrected. The authors, for example, in this case, forced every tool to return no evidence found, like a failure of a tool that will be used by an agent, and measured what happened. The loop accuracy dropped by 40.8 points for the React loop. So this is for the React loop. And it dropped by 29% for the ReWOO loop, not more. So it's not fragility. The issue comes from another different type of failure. So it's not the tool not working, it's actually something else. For example, the tool returning something that's not expected, which here should change the plan. So let's say your vendor changes their receipt format and you have hash E2, hash E1 here, and hash E2. And there is no step where anyone can reconsider between these two steps that were already planned by the planner, so which is problematic for you. So, and that's worse than actually a total failure of a tool that we already have seen previously. Because as we said already, when the planner plans something, there is no replanning phase. So to state it precisely, ReWOO tolerates a tool that fails. It cannot handle a tool that surprises. So this is called by limited adaptability when the plan is created up front. This was what the people who wrote the paper, the authors of the paper called it, limited adaptability. And actually the paper concedes the same thing from the other direction, where little context about the environment is available. Fully relying on foreseeable reasoning becomes impractical. So when, as we have seen here. So yeah, those are the two sides where your ReWOO loop should not be used and something else should be used. Now, one more descendant of the ReWOO loop is what we call the LLM compiler. And here, the whole plan exists up front. And what you're doing is that you're scheduling, like through the planner as usual. And you have a function calling planner. So this is the function calling planner. You have a task fetching unit here and the good old executor, which will be that part. What you're gonna do is basically you have the planner. It will emit a DAG. What is DAG is a dependency graph of tool calls. The task fetching unit streams out whatever is ready from here. So the executor does whatever it does, and then the task fetching unit would stream out like outputs, whatever here is ready. For example, you have task 1 and task 2 that have no dependency, so they fire at the same time. Task 3 needs both, so it has to wait. And that's the whole idea. So here the task fetching unit would give you the outputs of task 1 and task 2, and then would wait for task 3 when both are done. And the payoff verbatim is 3 points. First of all, latency speed up, and this is comparison compared to the React loop. So you're having 3.7 times more speed up, latency speed up. You have up to 6.7 times more savings, and an accuracy improvement of 9%. So you're almost winning on every side. Of course, the bars here are 3 different units, so you do not need to, don't focus on the lengths here. We're just trying to just give you a visualization, of course. This is the paper. It's from the ICML 2024. And notice that the speed up is made of, no, it's not new intelligence at all. So it's the same model, same tool calls, ordered better. So that's why the DAGs are so important, which is only possible because nobody is sitting there waiting for an observation before deciding the next step. And that's another important point for your reasoning. Okay, now to summarize, I'm going to put everything in one table. And here you have one piece of honesty. There is no single benchmark that compares these 3 head-to-head on a single test. So this is mechanics plus each paper own numbers, not a bake-off. So let's start with reflection. You have token shape. You have, of course, these are columns. The first one is pattern, token shape, latency, what you get, and where it breaks. So token shape is n trials. So each one a full attempt plus a reflection, multiplied by the number of attempts plus reflection. Latency serial, because trial 2 cannot start until trial 1 has been graded. There, what you get is large gains here, of course, but only with a real evaluator. You need the real life evaluator, of course. Where it breaks, no signal, no gain. This is very important. If you have no evaluator, then you're just looping for no reason. After that, we have the plan and execute. So it's one planner call, then cheap executor steps, plus a replan whenever reality deviates, which is nice improvement compared to reflection. Latency is spent up front. What you get is completeness and far fewer big model calls. Where it breaks is every replan buys back a big call. So here you have a volatile environment, and which raises your savings, the latency savings that you're making, your token savings that you're already making. So it's a trade-off. Now for the ReWOO, and you have one planner pass and workers parallelizable, the lowest latency and the lowest token bill of the 3. You have 5 times on tokens with 4% on HotpotQA on their benchmark here. Where it breaks is it cannot adapt to a surprise or a tool call that didn't work out as expected, or wrong result, which can actually really happen. Now, if you read the last column, because that is the actual, here, this is what's gonna make us take a decision on what's the architecture we're taking. You do not pick a pattern by its best case. You pick by which failure you can live with. Can you verify the outcome deterministically? Reflection, so if you can verify the outcome deterministically, reflection will earn its keep, which is really not. So this comes back to our debate about workflow versus multi-agentic systems. Generally, if you have a workflow that is stable and repeated, like actually, yeah. So yeah, here, if you have a workflow, then stable and repeated like end of batch, then plan and execute would be the better idea. Stable and you need it cheap at volume, then here you can use, if you have a stability, you have a stable workflow and it's cheap at volume, and even if there are some mistakes, it's not a big problem, then you could accept that ReWOO and that surprise can hurt you. So here, this is an engineering decision, of course. There is a name for the trade underneath all of this. And this is what we are doing here is spending compute at answer time rather than at training time. This is what we call test time compute. And O1 made it explicit. It thinks before it answers, and performance is consistently improves with more time spent thinking. So this is what we call test time compute. You're thinking before you answer, and performance constantly improves with more time spent thinking. So basically, it's the time spending thinking instead of already answering your question. So how good is that trait? So there was this paper from ICLR 2025, and it measured compute optimal strategy, and we are seeing that it is 4 times more efficient than best of n than a best of n baseline. And in a flops matched comparison, test time compute on a small model can outperform a model 14 times larger. But there is still a caveat here. Actually, the 4 times here is scoped to math, reasoning, and the 14 times holds where the small model already had non-trivial successes. Those are the two obvious caveats here. Now, and the family splits cleanly into, you have sequential, which extends one trajectory, and after that you're revising it. And that's basically what what we called already reflection, and that is why its trials cannot be parallelized because it's sequential, of course. Parallel, the idea here is sample many independent attempts, and basically you're doing a vote after that and best of n from earlier episodes. Which explains why these patterns feel like they are quietly fading. Reflection planning are the manual agent level version of what the reasoning model actually today is doing natively. You don't need to do it in a single code. This framing is basically mine. It is grounded in how the 2025 surveys classify these methods, but no single source states that it's cleanly doing that. So take it as my reading, not a citation. So, well, friends, before the recap, because 2 episodes now sound very alike, the evaluator optimizer from last episode is fixed roles that you coded, critiquing within single attempt. Reflection is the agent learning across trials through memory that persists between them. So it's same word, completely different unit of work. That distinction is my framing. Practitioners draw it the same way, but it's not really a formal academic taxonomy. It's just like some engineering convention here. Though you have 3 things to keep in mind. You have reflection needs a grader. The evaluator is the pattern. So a verifiable signal that gives you real gain and self-assessment, which will give you a token bill. Then planning buys completeness, not comprehension. It fixes missing steps, and each replan buys back a big call. And deleting the observation is the cheap one, of course. And there we are talking about the ReWOO, where you're having 5 times the token efficiency, parallelizable, and completely blind to any surprise that should have changed the plan. And that's the biggest issue of the ReWOO loop. Now, notice that every pattern in the series so far has been one agent tuned. Next episode, we add the second agent, and the failure modes stop being about tokens. Now, that will be episode 9, when agents talk to each other. See you there. And if you like the content, please like and subscribe. Follow me on LinkedIn. My name is Aldis Katapan. Ciao, ciao.